let's consider a new topic, thermal expansion. Thermal expansion. Under this topic, the candidate are expected to be able to determine the linear and volume expansivities. At the same time, the candidate should be able to access the effects and the application of thermal expansivities. They should be able to determine the relationship between different expansivities. At the same time, the students should be able to determine volume, apparent and real expansivities of liquids. Finally, the candidate should be able to analyze the anomalous expansion of water. Before we go into calculation, we are going to consider briefly what thermal expansion is all about. Expansion generally is increase in size of a material as a result of addition of heat energy. Addition of heat, HEAT. Expansion is increase in size, either in length or in breadth or in height. Increase in size of a material as a result of addition of heat. We are going to look at what are the advantages of expansion. Expansion is useful in burglar alarm. Number 2, also useful in fire alarm. Number 3, thermometer. In thermometer, it helps in keeping the temperature of a material constant. For example, electric iron. Then it is also useful in thermometry. We are going to talk about that when we get to temperature and its measurements. Then number 5, it is useful in a compensated pendulum. Then finally, it is also useful in the removal of tight glass stopper. And those are the advantages of expansion or expansivity. Let's look at the types of expansion. We have 3 types. We have what we call linear expansion. We also have what we call superficial expansion or expansivity. Then thirdly, we have cubical expansivity. We are going to take it one by one briefly. Linear expansion is increase in length. And when we are talking about linear is anything on a straight line. Okay, so increase in length is straight line. Only one dimension increases. Only one dimension increases, either the breadth or the length or the height. Then we have what we call superficial expansivity. For superficial expansivity, this is increase in height and breadth. We also call it area expansivity or area expansion. In this kind of expansivity, 2 dimension increases, either height and breadth. That is area expansivity. Thirdly, we have cubical expansivity. Increase in length, in breadth, and in height. And that's what we also call it volume expansivity or cubical expansivity. In this kind of expansion, 3 dimension increases. There is increase in the 3 dimension. Either that is length, breadth, and height. And those are the 3 types of expansion that we have. Now we are going to consider the formula or derivation for the 3 types of expansion. For number 1, for linear expansion, let's consider what we call linear expansivity. How do we define linear expansivity? Linear expansivity is defined as increase in length of a substance per unit length per degree temperature and per degree rise in temperature. From that definition, linear expansivity, this is alpha, is equal to change in length or increase in length per unit length. Per unit length, that is original length. Then per degree rise in temperature, that is temperature rise. Change in length, this is change in length, original length times change in temperature, change in temperature. That's what we are having for linear expansivity. Okay, which means we can let's call this one equation 1. Okay, our change in length can be equal to linear expansivity L naught change in temperature. Call it equation 2. Okay, then from there our change in length can be equal to final length minus original length. When we say change in something, that means final length minus original length. Okay, which is equal to our linear expansion, original length, change in temperature. Then let's derive a value for final length. Final length will be equal to, we are going to have the whole of this. This is minus, it will become plus L naught, which is equal to, something is common here, L naught. L naught, L naught. Okay, let's try and factorize this. This one will come out, open the bracket. After you have opened the bracket, you are going to have the whole of this plus 1. And that is a derivation for the final length. Okay, we can also have a derivation for final temperature. For final temperature, let's come from here. Okay, let's write the linear expansivity is equal to change in length, original length, times change in temperature. Okay, change in length will be equal to the whole of this again. Our change in temperature is equal to final temperature minus original temperature. Okay, let's put final temperature, change in the whole of this, let's put it in. We have linear expansivity, L naught, change in temperature, change in length. Let's make this change in temperature will be equal to change in length, okay, divided by linear expansivity, L naught. So let's introduce the value of this, which is final temperature minus original temperature, which is equal to change in length, all divided by this. Okay, then the value of final temperature now will now be equal to change in length, all divided by this. This is minus, it will become what? Plus. And that is a value, the formula to calculate the final temperature. So I'm going to make use of all this in our calculation. And that is all about linear expansivity. We will quickly go to superficial expansivity or area expansivity. For superficial expansivity, this is the symbol. We call it beta. For the one we have just considered, which is linear expansivity, we call it alpha. Okay, so for superficial expansivity, it has the same definition with that of linear expansivity. And superficial expansivity or area expansivity is defined as the increase in area per unit area per degree rise in temperature. The same thing, which is equal to increase in area per unit area, which is original area, then times temperature what? Change. Temperature change in temperature. The same thing. The change in area equal to our beta, original area, change in temperature. We can also know our final area. Okay? For change in area can also be written as final area minus original area will be equal to original change in temperature, so that final area will be equal to the whole of this original area change in temperature plus A naught, which is original area. Something is common, A naught is common, original area, into what you are going to have left is this and this plus 1, and that will be the value for final area. You can also derive a value for final temperature. The same thing we have done for linear expansivity, and that's all. So then we are going to quickly consider for cubical